Hello, this is Bryan Staley with the Environmental Research and Education Foundation. I'm going to talk to you today about advancing sustainable materials management, priorities, and pitfalls on the path to circularity. First, a little bit about EREF. If you haven't heard of us, our mission is to advance scientific research and create educational pathways that enable innovation in sustainable waste management practices. And we do that through a number of programs. We have a scholarship program, grants program, an internal program, which we call our data analysis program, as well as an educational program, which is part of what we're doing here. We have a number of different areas across the sustainable waste management spectrum, including climate change, emerging contaminants, and advancing circularity and recycling. And so with that background, I wanted to talk about circularity and material recovery. Typically, when we talk about these terms, the need behind this is to reduce climate change impacts affiliated with greenhouse gas emissions, reducing consumption of raw materials. Now, in order to fill these needs, the objectives are to eliminate waste and pollution, circulate products and materials, and regenerate nature. So when we think about being able to fulfill the needs with the objectives of eliminating waste, circulating products, and regenerating nature, that leads to a definition of a circular economy, which is a concept that envisions a framework for systems, solutions, and transformation that tackles global challenges like climate change, waste, pollution, and biodiversity loss. So that's really the basis for when we talk about circularity, this is what we're talking about. Now, one of the interesting things about circularity, and many people have probably seen graphics like this that talks about life cycle thinking and how we go from the process of mining materials or getting virgin materials, so these are our resources, going into a manufacturing process, delivering those goods that are made into the hands of consumers, and ultimately the consumers will use those materials and then dispose of something from that, which would lead to waste. The different influencers are shown here, but it's an array of different players. However, when we think about this, this provides really a more idealized concept of what circularity means. What does circularity really look like? When we think about what circularity really looks like, it really looks more like a pinwheel. There are various things that are spinning off at each portion of the life cycle, such as resources spinning off due to downcycling or burden shifting on the manufacturing process. There could be poor decision making for packaging design, or unrealistic or poor zero landfill or waste policies. On the delivery side, there could be inefficiencies there. And then for usage, of course, litter, wish cycling, which is putting things in a recycling bin that are not recyclable. And then lastly, weak or no end market demand for materials that are recovered that really have no place to go. And so in many respects, this creates a lot of challenges and limitations around the concept of circularity. And that's really what we want to focus on in the rest of our conversation today is what are these limitations and what are these different challenges? So when we think about some of the key points that we've covered so far, the transition to a circular economy requires a clear understanding of the flow of materials through society, what changes are needed to enhance circularity, and the potential environmental impacts associated with that. However, few have looked at the scientific knowledge, the data, or the operational knowledge that might be even needed to facilitate a greater circularity approach or a more circular economy. So therefore, the circular economy concept at this point, without this kind of data to help drive good decision making, can make the concept more aspirational than operational. And part of that is because the concept of 100% efficiency really is also something that's a bit more nebulous. It's hard to find a process anywhere in nature or something that is made by humans that is 100% efficient. So the chance of that kind of efficiency is slim. So in reality, no process allows for there to be a fully circular concept yet. Perhaps we'll get there. But these are critical points to be aware of as we talk about some of the limitations and efficiencies. Now, when we think about some of the limitations, it's important to note that our actions have environmental costs or burdens, and these burdens can detrimentally impact long-term sustainability. So efforts to improve sustainability are actions that reduce these costs or burdens. So ideally, we want to get to a zero burden type of situation, right? But what do we mean when we talk about burdens? These are things like global warming potential, water use, energy use, litter, the list goes on. So while circularity is justified by the reduction of raw materials and greenhouse gas emissions, sustainability refers to a broader array of scope and impacts. So therefore, it's important to note that circularity and sustainability are related, but they're not the same thing. So which of these are most important? Well, it all depends on what we're trying to manage. What kind of burden do we want to minimize or mitigate or have go away? And sometimes the answer to these questions might result in us making different decisions to reduce one burden, while ultimately that may negatively impact the ability to reduce another burden. So it's complicated and it can be nuanced. Now, when we think about what sustainability or circularity means in practice, a lot of times this boils down to what can we do as society to help improve sustainability or circularity. So practically, these efforts need to be demonstrable, actionable, and we've done lots of things over the past number of years to help us understand or help us take some of those actions. And some of these examples here just really tell us as society they're simple, they're clear. Oh, okay, if I take my bike to work, I can reduce emissions. I can recycle things. We want to go zero waste. But when we think about the different decisions that we can make as society, how can we be sure that these activities are beneficial? How do we measure these activities? And that leads to some concepts that we've been exploring in some of the research efforts that EREF has been undertaking to really evaluate how can we measure sustainability or circularity. And so this graph on the right shows a number of different recyclable materials: glass, metal, plastic, and paper or fiber. And so the way to look at this graph is that anything that is below zero indicates an emission savings. Anything that is above zero indicates something that is going to have more emissions than if we landfill the material overall. So what we see here is that not in every situation do we realize an emission savings when we recycle. And that's important to note because there can be situations where even though we're recycling the material, it may not be as sustainable as we think. And some of the factors that influence this would be things like product design, or where are we at even on the energy grid? Are we getting our energy from coal? Are we getting our energy from hydroelectric or wind? These matter. Transport distances matter as well, and ultimately where these recycled materials go matter. So all of these things are important. And we might see similar variability for other burdens. This one is just greenhouse gas emissions, but what if we're talking about water use? So all of these kinds of factors result in, again, a more complicated and nuanced conversation. So when we think about how we understand these limitations, it's important to note that the products that are manufactured and the consumer demand for specific products are really what dictate recoverability, circularity, and sustainability. Let me give you an example. When we think about consumer behavior, this is an important driver. And when we think about the 3 R's, or what I'm showing here is the 5 R's. What can we do? Refuse, reduce, reuse, repurpose, and recycle. If we think about what those actually mean as you read through those definitions, literally all of these are predicated by individual decisions. So these are things that we do, but ultimately we as consumers are a driver of the efficiency of circularity, if we want to think of it that way. And ultimately, the end use, where the material goes, does matter. So for example, if we think about the kinds of materials that are at our grocery stores. What the left graph shows is the different kinds of packaging that ultimately holds the foods and the drinks and the things that we consume as a society. And on the right side, it tells you where these materials are in the actual grocery store. But the key message between both of these graphs is that the vast majority of the packaging that exists in grocery stores is not recoverable. It's not recyclable. And so that is an important takeaway in that flexible film, for example, is the dominant material in most of the product categories that we see in these graphs. Yet the most recyclable materials, such as metal, glass, and fiber, represent the lowest portion of packaging. So what this means is that this limits what can be recovered before we even purchase the item. In other words, this is the hand that we've been dealt. and the hand that we've been dealt really dictates ultimately what can be recovered. And that's an important component to think about. Now, if we take this a step further and think about how do we as a society deal with things like food waste once we get it in our home. What we found in a study that we did in collaboration with Michigan State and Ameripen is that most food waste comes from foods with the shortest shelf life, less than 2 weeks, such as fruits and vegetables, prepared foods, and dairy materials. So factors that primarily influence food purchasing are not strongly correlated to extending shelf life or reducing waste. In fact, what are the things that influence us most? Well, it's the taste of the product and it's how much it costs. So when we think about the actual environmental footprint of these kinds of materials or packages, that's way down on the right side of the graph under slightly influential. How environmentally friendly the product is not our first consideration. We want it to taste good, and we want it to cost less, ideally. So that's an important consideration. What's the driver for circularity here is nowhere close to what's driving us in terms of our behavior. Now, once we have made that choice and we have placed something in the recycling bin, we many times will say, okay, great, I've done my part, it's in the recycling bin. And this is where things get interesting as well, because in many cases we assume that that plastic bottle, that PET bottle that we put in the recycling bin is going to be made back into a PET bottle. And some of that does happen. About 1/3 of PET bottles go back to PET bottles or are fully closed in terms of a fully closed loop. However, 2/3 of this material goes elsewhere, and some of it only has one recycle recycle cycle, which is basically means it's going to be recycled once and that's it. Examples would be PET bottles going to fibers or PET sheets or tape, things like that, where there's really one use afterwards. So you do get a recycle, but you do not get an unlimited recycle, which I think is the perspective that many of us may have. And so each end use has a different level of sustainability, benefit, and impact. And I think that's best illustrated with one of the most common, it's this sort of poster child of recycling, and that's glass. Glass tends to have about 7 end uses. Roughly half of them offer emission savings. What this graph here shows is a breakdown of those seven different end uses. Now, what you can see here is that the higher the bar, the more the savings of emissions. And you'll see that making glass back into glass containers or glass fibers or bricks all offer some emission savings. But if you look over towards the right side of the graph, using glass in like road aggregates, things like that for road construction or even filtration types of uses actually have no emission savings. It's actually worse than it would be to landfill the glass. So really what this illustrates is that the different kinds of end uses are really important if we're talking about sustainability and talking about greenhouse gas emissions or any other kind of environmental burden we might want to think about. The end use matters. The other aspect of this is if we think about end of life as an integrated system. End of life as an integrated system means when we go to put something in a recycling bin or we go to throw something away, we're not throwing away that one material. We're throwing away that one material with a lot of other different materials. And so these materials all end up in different bins. And so what's typically very common in North American households is that you'll have a bin. Most times will go to landfill. And you may have another situation where you have two bins, where one goes to landfill and one goes to recycling. A third bin, where that third bin has yard waste. So you have a three bin system. This is actually quite common across the vast majority of the population centers in the United States. And then in some more progressive areas, you may have a fourth bin that will accept food waste or for composting and those kinds of things. And so these are all mixed materials that are placed in different bins. And so again, we make the assumption that because we're placing it in different bins, then we should see a benefit in what we're putting in the recycling bin or the composting bin and so forth. So the end-of-life sustainability is based on an evaluation, though, of the integrated end-of-life options. It's not just a single endpoint or a single material. So what does that mean? And this table shows various scenarios that I just showed you and what that means for greenhouse gas emissions and diversion rate. So the assumption we commonly make is that if I can divert more from a landfill, that's going to realize better emissions savings. And so you may recall a few slides ago, I mentioned that the more negative the value is, the greater the emissions savings are. So what we're looking for here is the collection scenario that results in the most negative greenhouse gas emissions. In other words, the highest emission savings. And that's going to be actually a two-bin system. But when we think about then what's the option that gives us the most diversion from a landfill? Again, the assumption would be that it would be the two-bin system, but in fact, that's not the case. The system that gives us the largest diversion rate from a landfill is going to be a three-bin system. So this shows that even though we may be diverting more from landfill, that doesn't always equate to saving more greenhouse gas emissions. And so again, these are just important nuances to understand that ultimately, if we're talking about wanting to reduce an environmental burden, and we're measuring that based off of something like a landfill diversion rate, that doesn't always correlate well. So that leads us to, okay, if we're seeing this happening, then how do we create policies that can help us perhaps move the needle further? And recently, we've seen a lot of conversation around extended producer responsibility, or EPR. This is another type of policy construct that ideally will help us achieve greater circularity or greater sustainability. And the policies have been exploding across North America. One of the things we want to understand, and this is a study that we commissioned to really identify, does EPR as a policy scheme work? Is it something that can enhance the effectiveness of sustainability? Is it something that can make us more circular? A lot of the policies that are around for EPR really have not evaluated how effective it is, because we don't have a lot of data. So we went to the literature to understand, can we identify different studies that help us understand how effective EPR is. We thought we would find hundreds. We found actually very few, which was a little surprising. With all of the EPR frameworks being placed across different states and provinces across North America, there really haven't been too many studies that focus on the effectiveness of EPR. The articles we identified, these are scientific studies, only 7% talk about the effectiveness of EPR. There are 43% that are case studies. And ultimately, if we think about where these studies are happening, most are happening in Europe. Some are happening in the US, with a few in Canada. And so as we see this policy growth, and it does tend to focus on the different sides of the country, we see this explosion of different policy bills, both in the US and in Canada. So it is moving forward, which would tell us that this is a great tool, right? If it's exploding like it is, we should see that EPR is in fact a great option for us, and that's what we were wanting to evaluate in this. But what we found is that one, we don't have a lot of data so far to evaluate the effectiveness of EPR, and in fact, when we look at how EPR is being measured, we find some interesting anomalies, such as, this is an example from 4 provinces in Canada that are using recovery rate as one metric to evaluate EPR effectiveness. And in fact, these different metrics are based off of completely different KPIs. So for example, with Ontario, we're looking at the amount recycled versus the amount generated, whereas in British Columbia, it's the amount collected versus the market supply. These are not apples to apples numbers. So if we're trying to compare province to province, it makes it very difficult. And why do we care about comparing province to province or state to state? Because the types of materials that are being included in an extended producer responsibility policy are the kinds of products that are manufactured across the entire continent. If you buy a soda pop in California, it's going to be, generally speaking, in the same container as the soda pop you buy in Nova Scotia. And so these are the kinds of things that dictate we need to be measuring things off of the same kind of definition. Otherwise, it's really hard to compare apples to apples. And so when we think about the limitations of efficiencies, we can arrive at a number of different conclusions. Circularity and sustainability are not related. They're related, but not the same thing. Materials recovery effectiveness is largely dependent on decisions made by upstream product manufacturers. Our behavior which can be complex, and ultimately the end uses. And then lastly, that we have a significant lack of data. That's a pervasive issue, and that hinders the ability for us to really assess the impact and the effectiveness of sustainability efforts. Lastly, I'll hit a few challenges. With any road to improvement, uh, any kind of path we might go down increasing circularity, no doubt we're going to find some challenges along the way, and there are a few. So when we think about the recovery of materials at material recovery facilities or recycling facilities, one of the larger challenges that has come up in recent years is fires at these MRF facilities, which tend to be caused largely by things like lithium-ion batteries and other materials that can cause fires. Well, when you have a facility catching on fire, it can be very hard to use that facility to enhance the recovery of materials. And so that creates downtime. It creates additional costs. It can create challenges in insuring these kinds of facilities. And so this is certainly a bit of a roadblock in some cases to be able to enhance the recycling industry. Another thing is an emerging contaminant called PFAS, or forever chemicals. Many of you may have heard of these perfluoroalkyl substances, and this type of chemical is pervasive in society these days. It's used in hundreds of different consumer products, particularly in food and food packaging, which that food packaging could be highly recoverable. But that packaging also contains some of the highest concentrations of PFAS, which have been found to cause some potentially significant health issues. And so when we look at the kinds of products that can, or packaging that can contain PFAS, we see it's things like dessert and bread wrappers, sandwich and burger wrappers, paperboard like the French fry containers, and things like that. So these can all contribute to challenges in recovering materials, which can be problematic. So there was a case study that evaluated PFAS in packaging materials that went to compost facilities, and also looked at compost feedstock that did not contain these kinds of PFAS containing packaging. And the study showed that there was a significant difference between compost feedstock that had packaging and compost feedstock that did not have packaging, an order of magnitude higher in PFAS for the compost feedstock that had PFAS in the packaging. And that's why different composting organizations do not recommend that PFAS be in the feedstock. In fact, they actively work to screen that out. So the implication is that when you think about PFAS going into compost operations, and then you have this product that contains PFAS, that could potentially increase pollution potential, which would be a bad thing. And so PFAS is a hurdle to circularity because it basically creates limitations that result in materials that would otherwise be perfectly compostable going to landfill where they can't be composted, which is a challenge. So key points for challenges. Innovative or new products have the potential to create unintended consequences that should be considered when evaluating circularity and sustainability. Issues that significantly impact processing of recoverable materials have the potential to create substantial headwinds to circularity. Emerging contaminants like PFAS, they can affect the environment, cause health-related problems. That can also cause a problem. And lastly, low consumer education or uninformed decision-making. These are critical elements that can also reduce the ability to enhance recoverability. Thank you very much for listening. If you have any questions or would like to explore more resources, please visit our website.